Hi everyone, thank you for checking out our video. Today I'll talk about hardness of identity testing for restricted Boltzmann machines and POTS models. My name is Zongchen Chen and this is joint work with Antonio Blanca, Daniel Stefankovic, and Eric Vigoda. So we will study the undirected graphical models, which are widely used in the area of machine learning. And examples include restricted Boltzmann machine, Ising model, and POTS model. Let me first describe the problem of identity testing. Suppose that we are given a visible model M where all the structure and parameters are given explicitly. And meanwhile, we are also receiving some samples from hidden model M star, which we don't know. And our goal is to determine whether the two models are the same or not. So let's maybe first focus on an explicit example of graphical model, which is the restricted Boltzmann machine. The RBM can be thought of as the Ising model defined on bipartite graphs. Suppose that we have a graph G, and every configuration is an assignment of spins to vertices, and where every vertex will receive one of the two spins. So in most places, the spins are represented by plus or minus, but here I shall use the red and the blue dot to represent the two spins. And the Gibbs distribution for the Ising model is a probability distribution over all configurations, where every configuration will receive a weight, which is some exponential to some weighted sum of monochromatic edges. And here beta is an edge weight function, and z is the normalizing constant of the Gibbs distribution, which is also called the partition function. And this defines the Ising model. And if you furthermore let G to be a bipartite graph, then this is the restricted Boltzmann machine. So here is an specific example of RBM on a path of length 2 and 3 vertices. And you can see from the definition that when the beta of an edge is positive, then the two neighboring vertices are more likely to receive the same spin. And if it is negative, then they are more likely to receive opposite spins. And in particular, if all beta is positive, then the model is said to be ferromagnetic. And if all beta is negative, then it is said to be anti-ferromagnetic. And if there's no restriction, then we will call it mixed RBM. So here is a picture showing the problem of identity testing for RBMs. Suppose that we are getting some samples from a hidden RBM, which we only know the assignment of spins to vertices, but we don't know the graph and the beta. And also we are given a visible RBM, where both the graph and the beta are given explicitly. And we need to tell if these samples are come from the visible graph, the visible model or not. And we will work in the framework of property testing. That means we need to tell if their Gibbs distribution are the same or they are 1 minus epsilon away in the total variation distance. And in some paper, people also work on other distance like KL divergence or symmetric KL divergence. But here we will be focusing on showing hardness results. So we choose the smallest distance, the total variation distance, and this will also allow us to have the best hardness result. And before stating our results for testing, let me first discuss two closely related problems, which is the first one is the sampling problem, where you are given an RBM and you want to generate samples from its Gibbs distribution. And what we know is that for the ferromagnetic RBM, there is a polynomial time sampling algorithm. And by a classic result of Jerome and Sinclair, we have polynomial time sampler for all ferromagnetic Ising models and on all graphs, not only just bipartite graphs. And also by the symmetry property of RBM, we know that the anti-ferro case is also easy to sample. But The problem of sampling from RBM is NP-hard in general, even approximately. This is shown by Sun and Galanis, Stefankovic, and Vigoda. And there is a close relationship between sampling and testing. In fact, by a result of Daskalakis, Dikala, and Kamas in 2018, they show that if you have an efficient sampling algorithm, then you can use it to compute the marginal probability of every vertex and every edge, which will allow you to have an efficient identity testing algorithm. So combining the results of sampling, we know that for the ferromagnetic RBM, there is a polynomial times testing algorithm. And by symmetry, the same holds for the anti-ferro RBMs as well. So in the following, we will be focusing on mixed RBM. And the second closely related problem is the learning problem, which you can think of it as an inverse of the sampling problem. So in the sampling problem, you are giving the RBM and you want to generate samples. But now in the learning problem, you are giving the samples, but you don't know the RBM. And the goal is to recover the RBM from these samples. And this is also a classic problem that has been studied for many years, and it has attracted a lot of attention in recent years. And in 2015, Bressler gave the first n-squared log n running time algorithm for learning, but unfortunately, its running time is double exponential in beta d, where beta is the maximum edge weight and d is the maximum degree. And 1 year later, it was improved to n to the fourth log n and e to beta d. And finally, in 2017, Cliven's Mecha gave the n squared log n and e to beta t running time algorithm, which is optimal and matches the information theoretic lower bound. And afterwards, there's also a bunch of other learning results, either extends to other more general spin systems or consider different scenarios of learning problems. And there's a very simple implication from learning to testing. So basically, if you have a polynomial time learning algorithm, then for the testing problem, you can just take the sample from a hidden model and try to learn it. And then you just compare the learned model with the visible model so that you can do testing. So that means if you have efficient learning, then you also have efficient testing. And recall that the running time of the learning algorithm is exponential in beta d. So that means that like for mixed RBM, if beta d is order of log n, you have an efficient testing algorithm. And the starting point of our result is that we want to look at when beta d is larger than log n and see if we can do efficient testing. But what we actually show is that there is no polynomial time testing algorithm when beta d is little omega of log n. Here, little omega means that it increases faster than log n. So this is a surprising result because intuitively, one might think testing as an easier problem than learning, because for testing, you only need to tell if the samples from a given model or not. But for the learning problem, you need to learn from the samples, the explicit RBM, you need to learn the graph and learn the edge weight. But what we show is that as soon as your beta d is large enough, such that the learning algorithm of Cliven's Mecha became slow, you actually in the region that there is no polynomial time testing algorithm. And how we show this result is by a very general reduction from the counting problem to the testing problem. Here, counting problem is the problem of computing the partition function, which is polynomially equivalent to the sampling. And also our proof generalized to other classes of models like ferro RBMs, but with arbitrary vertex fields and the ferro pulse model. So in the remaining of the talk, I'll mainly discuss the pulse model and the main idea of the proof, which is the most innovative and interesting part of our result. And so for the pulse model is a very nature multi-spin generalization of the Ising model. So recall that for the easing model, every vertex receives one of the two spins, but now for the pulse model, it can has one of the Q colors. And the Gibbs distribution is defined in the same way. And for the ferromagnetic pulse model, we show similar behavior just like the mixed RBN. So when beta D is order of log n, you have efficient testing algorithms through learning algorithm. But when as soon as beta D is little omega of log n, you actually don't have polynomial time testing. And we do this by reduction from counting ferromagnetic pulse model, which are problems that conjecture not to have an FP-RAS. And the key ingredient in our reduction is the usage of the mean field pulse model. So let me first describe what is the mean field pulse model. So the mean field pulse model is basically the pulse model defined on complete graphs, and the edge weight is uniform and in the form of some constant beta over n. And what's interesting about the mean field is that there is some phase transition going on. So more specifically, you have a critical beta, beta C, such that when your beta is smaller than beta C, you are in the disorder phase, meaning that when you sample from the Gibbs distribution, you will see a configuration that looks like a uniform random coloring. So that means every color will receive roughly 1 over Q fraction of vertices. And however, when beta is greater than beta C, you will be in the majority phase. And when you sample from it, you will see most vertices receive the same color. So here in the picture, I use the red, but it can also be blue or green. But the point is that you will see one color dominates. And what makes it more interesting is that when beta is equal beta C, you actually see both scenarios. That means with constant probability, you will see the disorder phase, the picture on the left, and with some constant probability, you will see the majority phase, the picture on the right. And now going back to the reduction, recall that we need to construct we need to do some reduction from the counting to the testing, and we will take a hard instance of pulse model, and our goal is to compute the partition function of it. And what we will do is we need to construct a testing instance using it and feed it to the tester to conclude. And the way we do it is we take the graph G and attach it to a very huge mean field pulse model with the beta equal to the beta critical. And we will make this mean field sufficiently large so that the graph G will have only minor influence, some lower order influence on the mean field. That is the visible model. So that means that if your mean field is sufficiently large, the whole visible model behaves just like the mean field. So you will still see the disorder phase and also the majority phase. But what comes where G comes into play is that it will influence the ratio of the probability of seeing the two phases. In other words, if you know the ratio of the probability of the two phases, you can compute the partition function of the G. And for the hidden model, we will use the same graph, but with replacement of G with a complete graph on the same set of vertices. So this is a graph that favors the majority phase most. And we can show that for the hidden model, it's almost surely in the majority phase. And also it's easy to sample from it because most vertices will receive the same color. And if you feed these samples and the visible model to the tester, then the output of the tester is mainly tell you some bound on the ratio of the probability of the two phases, which will in turn give you some bound on the partition function. Now, if you also do some fluctuation of the beta of the mean field, then you can do some binary search on the partition function of ZG, which allows you to approximate it. So to summarize, we show that there is no polynomial time testing algorithm in the region that the learning program becomes hard, and we show it for many classes of graphical models. And more interestingly, we give a general reduction from the counting problem to the testing problem, and show some really close relationship of the two problems. And that's all for my talk. Thank you.